Okay, let's jump into it. Um, on behalf of Encord, I would like to thank everyone for taking the time to join us this afternoon and join the discussion on embeddings and evaluating them. We'll start off with some very quick introductions. I'm Oscar, one of the ML solutions engineers here at Encord, and we're very lucky today to be joined by my colleague Jim from the ML team. Jim, would you like to do a quick introduction on yourself and the kind of things you work on?
Hey all, I'm Jim. I'm here in the machine learning team at Encord, where I work as a machine learning engineer. So this means I kind of keep up to date and I stay abreast of modern ML trends, kind of working out where do our customers look for stuff, what kind of stuff is coming out, and then I also try and help shape the ML stuff within the platform.
Fantastic. Yes, and Jim is one of the key engineers on the TTI Eval repo, which is what we'll get on to today. But to start with, we're going to look at embeddings as a kind of general subject, what they are, how they use the different types, who the main players are, and then we're going to focus in on text image embeddings in particular. And then finally, we'll kind of move into the presentation section, which is this new TTI Eval repo, which is publicly available, open source for evaluating different text image embedding models. And Jim's going to give us a live demonstration of what that looks like and an example of how you can use it. So let's start from the beginning. Jim, when we say embeddings, what are they and what are they used for?
So kind of what an embedding is, well, at first, an embedding is just like a float, or rather a vector of floats. It is a Yeah, it is a point on which the machine learning model reasons. So these machine learning models, they take in input that's some media type. So we're working with images, and they will ultimately make a decision downstream. So a classic one will be a classification model that's working to distinguish cats and dogs. And so to that end, the model takes in a representation of the image and ultimately is making decisions. Now, when the model is making these decisions, the model kind of is going through, it has its layers that perform these operations, and it transforms kind of the raw input data. Here, like the raw input data would be like height, width, channels, just like the pixel representation of the data. But basically the idea being that kind of towards the end of the layers of the model, it's able to make strong, clear decisions based on the data. So like something that's classifying cats and dogs, it has the ability in that final layer, and the final layer is applying like quite a simple function. It can actually distinguish what is a cat and a dog is. And so that those vectors that have kind of gone all but one step, those are kind of taking the image to an embedding that can be distinguished and like represents a class really well. And the hope is that this is kind of a lower dimensional representation of the data that still kind of contains that semantic information. So in the case of being cats and dogs, no longer you've got this height width channels, pixel data. Instead, you've got something that's kind of pre-processed and yet has enough data to allow you to compare cats and dogs in a simple way.
Very cool. So it's like the kind of dimensionality reduction that our model goes through to extract this semantic information before it goes into the kind of final, whether it's classification or segmentation stage, right? Okay, very nice. And so I suppose then we need to kind of think like about the models that produce these embeddings and the
Mm-hmm.
different kinds of embeddings that we can look at. So I think that probably moves kind of nicely into what the main embedding models are,
Mm-hmm.
and yeah, and what they actually produce. What do these kind of a list of floats look like?
Mm-hmm. So kind of embedding models come, if you're working in a different area or a different modality, you'll have a different tool for a different job. And so kind of an obvious point being, if you're working with text, you'll have kind of textual embedding models, you're working image, and now even like for audio, people might be embedding audio if they want to like work out what song they're going to be interested in. But we'll kind of mostly just focusing on like image and kind of image and textual models. And so kind of here we have an example of like three top AI labs that have kind of shared either an open source, like a commercial embedding option. So OpenAI, the kind of the name of the business at the moment, very, very popular. They have some embedding models. They have their kind of text small, which is targeted text, and that will take text and embed it to like 500 dimensions. And then text large, which also can take text and image, which goes to about 1500 dimensions. Cohere, another company that's really kind of leaning into like the RAG craze going on at the moment, and all of these kind of vector database stuff. Very interesting stuff out of them. And then Google AI, they have kind of their open source offering. So this would be like PalyGemma as kind of a VLM. And then they also offer kind of Gemini, because they're like excellent embedding models that can do like actually can do video. There's some great examples of it, like video helping you find a particular frame, text and images, which you can kind of ping via their API and embed via that way. But kind of away from these commercial, like large lab settings, there are also the kind of the open source models. And so kind of the one that is the largest in the text to image field would be the clip model of like, which originally was shared by OpenAI back when they were a bit more open. So this was in 21, and that handles text and image in kind of an ambient way, which will kind of obviously be a large fraction of what we're talking about in this webinar. And then also Google AI, more on this kind of explicit embeddings. They released SIGLEP in November of last year, which is again like a really strong model that deals well with both textual and image embeddings.
That's very cool. You touched in there on the different kind of embedding lengths.
Mm-hmm.
I think that's when you were talking about the OpenAI model, that's a
Mm-hmm.
really interesting piece, right? Because I suppose intuitively, I feel like there ought to be some kind of trade-off between embedding length and then almost like embedding conciseness, and so kind of what does that trade-off look like in a kind of tangible sense?
Mm-hmm. So when you're like, I guess when you're consuming these embeddings, when you're working with any data, if you've got like a larger amount, so if you've got a large embedding, let's say like 2,000 dimensions, there is obviously capacity there for like expressing more information. It's a high dimensional space. You can kind of, with the intention being having these semantic notions represented, you've got more room for them to sit and it's more spacious. However, kind of from a computational point, it's like more laborious, more intensive to work with these larger embeddings because you're just simply working with larger data. So if you're looking for something that's kind of more efficient, perhaps, like, sorry, that's sort of fly, and there's more effective in some scenarios, having like a smaller one, which can work very well for the vast majority of applications.
That's really cool. That's really cool because I suppose that this is um, we're effectively working with taking one layer out of our deep learning dimensionality reduction process, right?
Mm-hmm.
Where we have this kind of sparse data set, and we're trying to extract the key semantic information. Um, and then I guess like a classification model would be the ultimate example of like pushing this all the way out into a kind of 0-1 score for a single class binary classification,
Mm-hmm.
where we're kind of reducing this right down to kind of one embedding. And so I suppose at these different levels, what are some of the industrial applications for these models? What are some of the things that we see our customers and other people in the field using these embedding models for?
Mm-hmm. So basically, these embedding models are an excellent way of kind of interacting with your data on a larger scale. Of say, let's say you were to go through and manually inspect, I don't know, 100,000 images or something, and you're going to struggle. Let's say I had 100,000 images of dogs. I would take quite a lot of time to try and distinguish these things. Were I to have an embedding model, I can kind of point at this data, go off and make the embeddings, and then I have the capacity to, and these are kind of two notions I'll expand upon, do like a natural language search on these things, or kind of do an embedding-based similarity search. The former being, if I want to look at, well, I'm not very good at dogs, dachshunds or sausage dogs, be able to textually similarity search these things. So this is the benefit of models such as CLIP, such as SIGLET, these kind of multimodal ones. You can embed your images and then embed the text and also basically do a similarity search using these two different things. And that would allow you to kind of out of the box suddenly create your data to an excellent degree. And then also you can just similarity search kind of image to image on, I have found a dachshund I love. It's adorable, and I want to find other cute dogs like it. And so I would go and I could do a similarity search based on that embedding, where you're kind of in the embedding space, you're looking for near points, for some notion of near. And the idea being because these embeddings encapsulate the semantic information you care about, the nearby points kind of in the space have alike properties. And so the idea being these embedding models are trained to kind of bring alike to alike and then dissimilar to dissimilar.
And that's really interesting when you say alike to alike. So I suppose then, much like people, where we kind of have generalists and specialists and people who are kind of experts in a particular field. If we're just looking at extracting, if we're looking at finding all the dogs in our data set, that's quite a broad category. If you're somebody who's really into dogs, then right. But then, as you mentioned, we need to find a way to kind of give this like domain specific information to these embedding models such that they can extract whatever semantic information is key to our use cases. So I
Mm.
think this is like what we mean when we talk about fine tuning. Do you want to just kind of add some color to that, Jim?
Mhm. So these models like are very impressive. They do very well kind of across the broad spectrum of cases. They work very well out of the box at a whole host of tasks. But as you say, if you're kind of you and personally have an interest in a distinction that won't be encapsulated in these models, like they, aren't going to be able to distinguish minor dog breeds, the degree you care about, to continue on my other example. You will basically want to be kind of telling the model and encapsulating, I care about these distinctions. To me, these contain different semantic information, more so than has been represented in the model's like training corpus. And so that would be fine tuning. Kind of the reason you do this fine tuning is the model is very good. The model has kind of proven to have the capacity to produce quality embeddings, like be it for similarity search, like textual embeddings, or whatever kind of your uses downstream of the embeddings are. But you want to like improve that capacity for your niche case. And so to do that, fine tuning in practice is you would continue the training process. You're kind of trying to burn in this new information. So you might kind of bump up the learning rate compared to like the pre-training so that you're kind of able to more efficiently dictate these kind of new value set or whatever, so that you can kind of dig in and introduce the notions that you care about, and the idea being that you'll get notably better performance.
That's really cool. I think there was something that came out of Meta's research lab that compared these models' ability to generalize and specialize, and there was a kind of direct trade-off between the performance. We have the models that we were looking at on the previous slide, which are maybe trained on kind of benchmark data sets and are very good at general distinction. But when we have these kind of domain-specific use cases, then we need to fine-tune our models so that they can specialize and focus in on a particular area. I mean, we've talked about kind of dogs as an example, right? But what are some of the kind of like industrial examples that we see there that are important?
So, kind of from what we've seen here at Encord, a lot of customers might be particularly interested in, say, like sport. I don't know, they want to distinguish the striker from the midfielder. They want to distinguish the batter or the first baseman from third baseman. That's a common example. Another scenario would be kind of, let's say, like actually industrial applications. If you're kind of interested in like inside of a factory warehouse, for example, distinguishing certain elements there. And we've also seen a particular kind of interest from like the medical community, wherein if you've got a generic off-the-shelf embeddings model, and we trained kind of on a representative set from the internet, which is very impressive, but it kind of deals with stuff. If we look at our slides, more so on the left, kind of on a human scale. But if you're in a medical domain, you have kind of very technical and very hard to distinguish information that might be on that slide on the right that nor the embeddings model will be able to distinguish out of the box. But by trying to like introduce this information and like burn it in a stronger way, you can, and we've seen people basically make further distinctions and improve their embeddings so that for their scenario, kind of the distinctions they're interested in, they get a improved embedding.
I see. And I suppose this process of fine tuning is reasonably intensive as far as computation goes.
Mm-hmm.
And then the information that we're discussing extracting isn't as simple as the kind of binary classification task that I mentioned earlier. We can't just say, is it right? We need to be able to compare these different model performances and say, was my fine tuning worth it? Does this model have the desired effect? of better extracting the key semantic information. And so how do we do that at the moment?
Mhm. So, as you kind of correctly identified, fine-tuning these models is quite an intensive process, both like from a technical point of view and also kind of, I guess, from like a computational overhead. Obviously, the original training of these Nile magic models was a pretty impressive feat. Like it's taken, exhaustive amount of compute hours, exhaustive amount of data, and so to try and like continue to bring that in takes a bit of know-how. And then how do you actually distinguish that all your effort's been for good? How do you distinguish that when you go on to use these embeddings, will they be improved? And so that was kind of what we were working on here at Encode. We were like looking at embeddings, kind of doing some fine tuning, and we were like, but we keep constantly need to do these evaluations. And you can see papers where people are working on embedding models, and they are evaluating the embedding models and they'll compare it against the literature, but it's always quite an involved task, and we were noticing the same. And so that's why we worked on TTI Eval of having done this fine tuning, train these models, and then wanting to compare them against open source models, compare them against like closed source models on a variety of data sets. It was basically useful to have a tool wherein it was a bit more plug and play for us. So now we were able to kind of the fine tuning to evaluation process could be made a lot more cohesive.
Very nice. And I think we've got an example of one of the plots that we can generate using the using the TTI Eval repo, right? So
Mm-hmm.
this is an example of when we're looking at two different clusterings between a kind of more general model and then a fine-tuned one. And Jim, yeah, just talk us through this plot, what we're looking at, and the comparison between the two sides.
Mm-hmm. So broadly, kind of the scenario and data set we were looking at here was geospatial data. So I actually worked on this model a few months ago now, and kind of you can see from the legend there on the right, like airport, beach, church, commercial. These are like I don't know geospatial features. So the data set we were working with were these like satellite photo shots of quality image caption data. So here we were kind of fine tuning and comparing against these text and image embedding models. And so not only did the data set itself kind of have a class, they also came with captions. So like an airport might be this is a satellite picture of an airport. There is two hangars. There is a plane on the runway and some luggage approaching the plane. And so this is kind of conducive and alike to the data that was originally used to train this like clip style models. And so meant that the fine tuning process was able to kind of keep the ability to, in natural language, converse about embeddings. So have cohesive image and textual embeddings. But back to the plot, as we are looking at it now, this was the reduction of the embeddings created with the fine-tuned model. And as we transition to this stage, this is a tiny clips. This is an open source kind of like world model. So this RSCI encode, you can kind of tell there's a better distinguishing between classes. So the colors represent classes and the colors are more separated and more in small clusters. Whereas here, there's a lot more modeling. It's harder to tell kind of what's what. And so when you're using like these embeddings for your, let's say I'm doing a similarity search, I'm looking for airports, with the RSID encode model, I would feel like a lot more comfortable. I would just see that when I search for airports, I'm getting other airports. Whereas kind of as to be expected, like with a tiny clip model, satellite images not being its forte, it kind of visually this represents that it won't be producing embeddings that is clearly distinguishable.
It's very cool. Very cool. And this is just kind of one example of a visualization that we can produce from the repo. But I think now, Jim, you're gonna maybe take over and give us an example of some of the other metrics that we can generate using the repo and also comparing different models and data sets in Liu as well, which
Mm-hmm.
is very exciting stuff.
Mm-hmm.
I'll let you share.
Q. Cool. You should now be able to see my screen. So which
Yep.
is on the repo. So this is sorry, it's hard for me to balance seeing the bottom of the screen I'm sharing on, and you all see my lovely face. But now looking at the repo, this is as we said, it's an open source repo. Here it is, and this basically shows off some of the features if you want to come and use it. Following this webinar, if you want to basically use it to evaluate your own embeddings, it's here, and yeah. So examples, this is, we can create the animations such as shown earlier in the slides, and there'll be another one to come. And also you have the capacity to create these like representative graphs that show kind of a cross model, cross data set, what kind of performance you get. And yeah, we are worth remarking. This is designed to work with kind of cross data set, cross model. And so for that means here we have a variety of data sets that are, some are available in Hugging Face, which if you're not aware of is kind of a very, very popular open source kind of community for ML stuff. So they share data sets, they share models. And here we found some data sets and we support them, but we support other data sets from Hugging Face. And here is an example of a data set that is within our own core platform. And so it's access to that. And additionally, we have access to models. And so here's quite a strong variety of models. We have access to models that are kind of open clip. So these are like, it was kind of two bifurcation of clip architectures. So originally it came out from OpenAI, and people kind of have built upon that, or there's kind of an open clip where they did a direct reproduction. OpenAI and clip was very, very good. I'd say now, and as we sit in 2024, probably not state of the art anymore. However, like it actually did take quite a few years for the open source community to be able to compete with clip. Like the architecture was distributed widely, but they kept the data set to themselves, was very much like their forte now. And yeah, it took quite a bit of effort. Meta like actually released a paper on like how data curation against training that architecture can produce a clip model that's slightly better. But this is like a selection of models that we support, and it includes SIGLIP, which I would say now is like kind of the best in class, and it also includes our RSCID encode. And so now, kind of showing off a little demo. Here is a notebook that I'll be using for the purpose of the demo, and basically it's fairly straightforward. You can just install the repo. These embeddings and their dependencies or whatnot are like quite computationally expensive. So unfortunately, during the slide demo, I won't be generating the fresh embeddings and the fresh evaluation, but we'll be at least walk through the notebook that I was kind of working with. And so here, the example will be working with a fashion data set. And so getting out of our in-core platform, we have our fashion data set. And now when you're using the TTI Eval, you kind of work with model data set pairs, as kind of mentioned previously. So in terms of models, I'm kind of data set saying constant, you want to kind of build the embeddings against each one. And so model, 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 working with a fine-tuned specialist fashion model, kind of the generic clip that is the kind of your out-of-the-box solution that works, as we've discussed, across the spectrum, and here kind of an open clip of a certain like capacity, certain size. And you can see there's some downloading and some whatnot. And then when it comes to evaluation, we evaluate our models, and here are a few different metrics. So I'm going to basically walk us through now what these four different metrics represent. So zero shot is if you were using it kind of as a texture model, how good am I at like my text ending up near my image? So if you're kind of, for our fashion data set, we have classes. And basically, if we're looking at dresses, we want to see when we embed the class name dress into the example, do we find that it sits near example image dresses in kind of our test set? So for zero shot, we actually see our clip, fashion, and vet all perform one very close to each other, but two, we actually see the fashion doesn't necessarily perform best at the back, but actually we can see on our other metrics, we do find that fashion is performing better. And I'll kind of walk us into the other metrics.
Just so just to kind of
Mhm.
take a step back for a second. So this is other, and you've pre-run this because of the kind of heavy computation side, so we don't have that kind of fresh embedding smell. But this is all publicly available and open source. I know we've mentioned that some of the data sets that one of the data sets was available through Encord, but a lot of them are open source too. And so this is a tool for people who are for anyone who is developing their own embeddings, comparing them side by side, and then these are the kind of different metrics that we can use to distinguish by dataset and by model. And so we can see that CLI command where we're literally just calling in our different models and our different data sets to be able to do a kind of side by side comparison, right?
Yeah. Sorry, because like here we can see the production of the embeddings takes just multiple minutes, and so I thought for the brevity and I don't know about wherever it is, but here in London it's hot today, so I thought a hot Thursday afternoon, didn't want to keep everyone around to watch me stare at a loading screen. But kind of getting back to the metrics, the linear probe, this is quite a fun one. So when you've got your embeddings, linear probe is checking basically are the classes linearly separable. So where I've got my dresses, where I've got my skirts, my t-shirts, my trousers, can you basically have a plane, a linear separation that separates the classes? And here we see fashion kind of does perform the best. And this is, if you're like thinking about maybe a similarity search, this is conducive to that, as is our next one, which perhaps even sits closer to how similarity search works. Of this WKNN is our weighted K nearest neighbors. So K nearest neighbors is kind of, we vary K and we're trying to check if you take an image and you look at its nearest neighbors in the embedding space, are its nearest neighbors of the same class as it? The idea being that they are kind of sitting, if we recall, or we look ahead at our embedding plot, we want images from the same class to end up sitting near each other. We want them to kind of be represented in clusters. And this is basically applying a clustering algorithm. Is that the case? The clusters sitting in kind of their own class. And here we have fashion leading the pack. And if you think about how similarity search works in practice, of taking a point, looking at its nearest neighbors, having quality or a strong metric for weighted K nearest neighbors can translate to like having good similarity search. And our final metric is image to image retrieval, which is quite fun. If you basically are taking an image and then you're doing a search based on it, are you finding things nearby that are of a similar class to you? So it's quite closely linked to weighted K nearest neighbors, but it's not quite the same notion. And also, kind of as we've seen in the slides, this is here comparing kind of the clip fashion data set and the real fashion data set. I can animate and I can produce the reduction. So we're translating now to the clip. Actually, first I'll walk through the legend. So our classes, this is again from the fashion data set. Here is a selection of the classes in the data set. So, outerwear, dress, bottom, and it's colored based on that. And kind of here in clip, amongst these items, they're kind of different colors. So perhaps dress and outerwear, but they're not quite as well distinguished as we see here in the fashion data set. Sorry, fashion model rather. Do you have any questions, Oscar?
No, I think it's really nice to be able to compare the kind of empirical metrics with the visualization in one view. And yeah, interesting. Kind of reminds me of when you were talking about the clip model earlier, and you said that kind of OpenAI have kept their data set private that they use to train the model, despite the architecture being public, and it's just more kind of emphasis on the importance of data set over architecture, perhaps in developing these models. And yeah, this is it's really nice that you can kind of have these two different views to look at the different models and their performance across the data set, and even by class, because I suppose in this case, some of our classes may be more important to our model's performance in practice than others. So being able to look at these here as well is really helpful.
Absolutely, yeah. If you're particularly interested in women's fashion, the distinction between a dress and a skirt might be more important to you. But or just kind of anything in practice, you might care more about distinguishing the embeddings. But now
Absolutely.
to kind of show what it's like in practice, working with, if we've kind of decided that these fashion embeddings kind of, according to our metrics and according to looking at the reduction, they kind of look cleaner. I'm going to show what it's like using these embeddings. And for that, I'll be showing what they look like within the Encode Active platform. So here I've got two projects that are one.
Jim, maybe we should give just in case anybody isn't familiar with the platform,
Okay.
in 60 seconds. OnCode Active is our data curation, model monitoring, and evaluation platform. So this is really the kind of hub for active learning from a kind of data development point of view. And so yeah, this is there's the ability to import your own embeddings and then compare the different clustering and how these perform on similarity search in order to find the key elements of your data set to prioritize for your machine learning challenges. And so that's one of the key reasons why this repo is so helpful if we're faced with millions of images or on the scale of hundreds of millions, then what we can do is we can identify key images that relate to other ones, so we can ensure we have representation across our different trained test and validation splits,
Mhm.
and also just ensure that we're identifying the key failure modes and points in our model that are most important.
Yeah, absolutely. Kind of a great purpose of active is you're working with a vast data set. You kind of you're going to want to be perhaps labeling some of them ultimately, but you want to be kind of knowing and distinguishing from the get-go what kind of where are the edge cases of the data set, what's kind of looking like representatively, kind of get an interactive engagement with it. And we find that embeddings is kind of a great way of kind of on a large level engaging with your data set and just starting to product it and see what it feels like. So here, this is kind of using the encode embedding model. So we have the embeddings here, and here is the kind of the custom embeddings. This is working with the fashion model. I have the embeddings here. Yeah, there they are. They arrived eventually. And yeah, so kind of on this level, it can be maybe slightly harder to gauge how certain embeddings are performing. However, I were to go back and in this scenario, kind of looking at my fashion data set, I am pretty interested in like certain items. And so for me, my mind, I immediately fell to this key. So I really like the look of and the style of this. And so when I say key, sorry, key styled necklace. And I'm perhaps interested in having items that I'm looking for that's similar to this one. So I might go and do a similarity search here based on like the custom embeddings. And again, using our encode embedding model, which is more of kind of like the world level model that we've discussed previously. It's not a specialized model. There's kind of not as much expectation that's going to perform well for these fashion interest. And so here I've done a similarity search. I've kind of looked at this key necklace that's like key necklace perhaps, and it's yeah, it kind of fits the vision of what I have for my upcoming like fashion book. And so I see, oh, I've looked for this. I'm kind of getting other necklaces. I'm getting other items, and I've noticed that this kind of earring now that has kind of a similar, almost like crown shape, kind of also matches that vision. Of it's in a sense that if I were to look with the encode embedding model, I actually don't quite doesn't quite arrive. Like these items are silver, they are diamonds, I imagine, and they look great, but they're not the vision that I was trying to create for my data set. And so this exactly is a scenario where kind of having made these custom embeddings, having evaluated them and seen like quantifiably, they sit better when I'm trying to like actually create my data set and I use embeddings for that purpose. I'm seeing that using these custom embeddings, I get like a immediate impact in terms of now I can see, oh, I look for certain items. I'm notably getting items that are more matching the vision that I care about.
Very cool. Yeah, and so I think it's very nice to be able to evaluate how these embeddings are performing before we can go about curating our data and be able to compare across different data sets. And we can see that the kind of general world model isn't quite extracting that same key semantic information.
Mm-hmm.
Should also note that this is operating across like tens of thousands of frames, right? So this is rapidly identifying the key kind of images in our data set that correspond into these like collections.
Mm-hmm. Absolutely. So, like working with over 30,000 frames, finding this item, ruffling through a drawer almost, it would have taken me quite a while. Whereas now I can even continue, and now I'm searching using the two items, and I'm kind of even further going down this key crown train, and I'm getting like impressive stuff. Whereas if I was here, I'd kind of, oh, now I've looked, eventually I can find it. But if I continue down this train, I'm still maybe in the right ballpark, but at least personally, I feel like when I'm using this custom embedding, you can kind of see that the like responses you're getting just fit more to the vision I have.
Fantastic. No, that's great, Jim. And yeah, and so I guess if we were building out a full winter prediction model and we were trying to optimize our kind of design choices for this full winter, then we'd be better set with our fashion embedding model.
Mhm.
That's great. So I think the last section of this session is going to be around Q&As. So if anyone in the audience has any questions for Jim, then please share them in the channel and we can pass them on. And okay, we've had one on what is the scenario where custom embeddings have produced the most value?
Okay, cool. Coming back to kind of what we mentioned previously, medical is like a huge case where kind of you would think it, right? Like medical is, minor differences that are kind of massively out of the scale of like human experience do have like a massively different meaning in that context of like, yeah, with a brain scan is very different to the generic image that these world models will be trained on. When I'm looking, like various caption pictures from the internet might tend to be various caption pictures of cats, but a brain scan requires like a much greater fidelity to distinguish things. And so that is absolutely a scenario where we're kind of seeing customers particularly be interested in. And like you also see kind of in the open source and the academic community, that people are very interested in having specialized embedding models. And another scenario is kind of maybe, as again mentioned, these geospatial things of like, whilst the training corpus for these large embedding models is nice, is like it's reasonable, it is kind of as we humans see the world to a degree, and I don't tend to be a looking down from the sky. And so when you're interested in particularly distinguishing things from a bird's eye view, that is a scenario where we've noticed, and people do have like various models for kind of working and distinguishing bird's eye view images.
I suppose that's kind of you could extrapolate that to any domain where a sort of general human expertise would fail, then fine tuning in these custom embeddings could be advantageous. Don't know if
Yeah.
that's too broad a brush.
Um, I mean, in practice, that's kind of what's observed of if it's, yeah, as you say, a domain wherein like you would require, you know, specialist knowledge, you'd require actually kind of some training or some understanding of the scenario of itself that wouldn't be expected to be uncovered by like average Joe on the block rather. And yeah, so that would be provides like endless scenarios wherein having fine-tuned, having custom models like allows for improvement.
Very cool. And now looking forward, we have had a question on the future of the TTI Eval repo, Jim. Do you plan on extending TTI Eval to evaluate other Gen AI models that aren't text to image?
It may potentially be on the cards. Kind of what we've been, at least recently, most working on Encode has kind of been like textual and image models. Whereas like now we're kind of maybe looking towards more audio applications and potentially video. And so kind of maybe based on like what we see in feedback, and obviously the repo is open source. And so I'm loath to say, if obviously if you're interested in such things, you're welcome to kind of get stuck in and see if you can introduce such things. But yeah, like depending on internally kind of what we're interested in and what's we're seeing, and then also kind of from the customers and the people we talk to, if we do see that particularly people are interested in certain evaluations, and that's definitely something we could consider.
Very cool. Exciting stuff. Yeah, multimodality is definitely a very exciting space that we are moving headfirst into. And I think like we'll finish on this kind of last question that we've had in on the future of embeddings in AI more generally, Jim.
Mhm.
Like, how do you think? How good will these embeddings get? Where do you see them going? Give us a kind of a prognosis from your expert opinion.
Ooh. I think embeddings, we've only seen improve, and so I imagine they will continue to improve. But they are improving like relative to like I don't know laws of nature. So kind of what we notice at the moment, the behavior being that world models do perform very well on a world level. They will continue to do that. But we're also seeing kind of the specialist models people are pursuing and are continuing to pursue. They will continue to allow kind of this differentiated performance. So if you're, think of it a video game, you're allocating skill points. I mean, I could be tempted to say the world is leveling up. We have access to more resources, more know-how, more data, and we're getting more skill points to allocate. But like, we will continue to see people allocating their skill points down certain avenues. But I am very excited to see about where embeddings go. Like, NVIDIA kind of over the last 2 weeks released like a purely imaging-based model that is kind of almost introduces a new Pareto boundary. So in terms of like the efficiency of the embeddings it produces and like the quality of them at each like scale. So if you're like looking for something like tiny and you're really interested in images, basically we're continuing to see there are improvements. And so we can only hope that there will continue to be improvements.
Fantastic. I think that wraps things up really nicely. Thank you everyone again for joining today. I hope you found the session useful. Make sure to start the TTI Eval repo and leave any kind of notes or feedback on there. And yeah, if you have any more questions for either of us after this, if anything comes to you, then please don't hesitate to get in touch with myself or Jim. And with that, we will see you at next month's webinar.
Thank
Thanks,
you.
everybody.
Take care.